working on the last portion of exam review. Number 16. Describe the bonding in the following molecule using valence bond theory. Include labeled atomic orbital and hybridized orbital diagram and explain the reasoning. Make a sketch of the orbitals overlapping sigma pi hybridized orbitals and make sure you include any lone pairs. So the best thing to do when you're trying to draw a scheme of hybridization for valence bond theory is to first have a Lewis structure so you can see how things are bonding. So essentially here's kind of the order of the arrangement of the atom. So you have the nitrogen, carbon, carbon with 2 hydrogens, then an oxygen, and then a hydrogen. Let's connect the dots and fill the lone pairs. Well, I know that since carbon wants 4, I can make 2 more bonds with the nitrogen and give the nitrogen the lone pair, and then give my oxygen the lone pair. Awesome. So now how many central atoms do I have? So how many hybridizations could I have? I have 1, 2, 3 central atoms. So I'm going to have 3 types of hybridization. I can look at my carbon here, and I know my carbon is 2s and 2p. My 2s and my 2p will hybridize. But what is the hybridization that I need? This has 2 electron groups. This is a linear geometry. So these will hybridize to form sp to give me my 2 electrons in my geometry with my p unhybridized to give me my triple bond. What about this one? This is 1, 2, 3, 4. So this would be sp3. So my carbon would hybridize to form 4 sp3 structures to give me my tetrahedral shape. Then what about my oxygen? My oxygen is bent, but it's still sp3. So oxygen is 2s2, 2p4. So these will hybridize to give me my electron geometry of 4 things around it for sp3. Then I fill my electrons where these represent my lone pairs for my 6, and here are my 2 that will bond with my 2 hydrogens. Perfect. So now I've described all of the ways that the orbitals will hybridize. Let's draw the structure. So I have my nitrogen, my carbon, carbon, oxygen, hydrogen, a hydrogen up here, a hydrogen up here. So I will have my sp orbital, my hybridized orbital in green. That's going to overlap with my sp3 orbitals of my carbon. Oh, I forgot my hydrogens are here. And the oxygen. And then the oxygen will, let me get a blue, will then have the sp3 orbitals that have the lone pairs and overlap with the hydrogen. So then my p orbitals will overlap with the sp of the carbon and make a pi bond for my triple bond, but 2 pi bonds. So I want to label this. This is my sigma of NP with carbon sp. And these are my pi orbitals of the NP orbital with my carbon p orbital. This is a sigma with carbon sp and carbon sp3. My hydrogens will overlap as well. Both of them have sigma with hydrogen s and carbon sp3. Here is a sigma with carbon sp3 and oxygen sp3. My lone pairs are in my oxygens, which don't have bonding, and then there's one more sigma bond with my oxygen sp3 and my hydrogen s. And there you've explained all of the bonding, how the electrons are actually overlapping together, giving you the different bonds that you have. And you can fill your electrons in to show. Alrighty. In Vesper Theory, which uses the Lewis model to determine molecular geometry, the trend of decreasing bond angles in CH4, NH3, and H2O, so methane, ammonia, and water, is accounted for by greater repulsion of lone pair electrons compared to bonding pair electrons. So we know that Vesper Theory is another step from Lewis theory by taking into account the repulsion of the bond electrons and lone pair electrons. How would this trend be accounted for in valence bond theory? So the way that we should look at this is, let's draw 4 Lewis structures. So I have CH4, NH3. I even forgot the question because I read so fast. I'm going to reread it. So in Vesper Theory, which uses the Lewis model to determine molecular geometry, the decreasing bond angles happens because of greater repulsion. So this is tetrahedral, right? 109.5. Now, because of this lone pair, this decreases a little bit less than 109.5. Then, because in water there's even more lone pairs, it decreases even more. So that's that first part. How can this trend be accounted for in valence bond theory? So all of these have what type of hybridization? They all have sp3, 1, 2, 3, 4, to give that geometry hybridization. When all 4 hybrid orbitals form bonding pairs, the bond angle is 109.5. When lone pairs are present, they lower the tendency of the central atom to hybridize. As the number of lone pairs increases, the bond angle decreases, as we've seen here, moving closer to the unhybridized bond angle. This causes bond angles to decrease with increasing number of lone pairs on the central atom. So when all 4 hybrid orbitals form bonding pairs, the bond angle is 109.5. When lone pairs are present, they lower the tendency of the central atom to hybridize. So the hybridization is harder to do with lone pairs because of that decrease in bond angles. This is how it relates. As the number of lone pairs goes up, the bond angle will decrease, moving closer to the unhybridized orbital of 90 degrees. This causes the bond angle to decrease with increasing number of lone pairs on the central atom. Last question. Calculate the heat of the reaction for the combustion of octane, a component of gasoline, using the average bond energies, and then calculate using the enthalpies of formation. What is the percent difference between your results? Which result would you expect to be more accurate? So this way, you use the heat of formation, which you would look up, are given to you on the front page of this. And then here you use the bond dissociation energy. So let's do the heat of the reaction using the heat of formations first. So first we need to write the balanced reaction. C8H18 plus O2. Now, how did I know that octane was a liquid? I know it's a liquid, and this comes important when you're looking up your delta H values, is because it's a gasoline. So you balance your equation, take a moment to balance. I would pause the video. I get 2, 25, 16, 18. So then for the heat of the formation reaction, you take the enthalpy of the reaction is equal to the sum of the products minus reactants. So on the cover page, I know that my heat of my reaction for carbon dioxide is negative 393.5. For water is negative 241.82. For oxygen is 0. And for octane is negative 250. So I would take my 16 moles of CO2 times negative 393.5 plus 18 moles, this is in kilojoules per mole, times negative 241.82. That's my products. Subtract that from my reactants. Well, I have 25 moles times 0 kilojoules per mole for oxygen, so that'll just cancel, plus 2 moles of octane times negative 250 kilojoules per mole. That is equal to negative 5,074.38 kilojoules. Awesome. So that's one answer. Then you want to solve it using the bond dissociation energies. So you would look at your table of all the bonds and figure out how many you have. So octane has how many bonds? I have 1, 2, 3, 4, 5, 6, 7, 8 carbons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So I have 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7 bonds. Even though I have 8 carbons, I have 7 bonds of the carbon-carbon bond, but I have 2 here for my coefficient, so I have 14 carbon-to-carbon bonds. I know that this delta H of reaction is the sum of bond dissociation energies of my products plus the sum of the bond dissociation energy of my products and reactants. So carbon to carbon 14 plus how many hydrogens do I have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. 2 of them, so 36 carbon hydrogen. Plus O2. Well, O is double bonded to another O, but there's 25 of them, so 25 oxygen-oxygen bonds. And that's going to sum to carbon dioxide. Carbon dioxide has, it's on its own, 2 carbon-oxygen bonds. And then I have 16 total, so I have 32. So 32 carbon-oxygen bonds plus water has 2 oxygen-hydrogen bonds, but there's 18, so 36 oxygen-hydrogen bonds. Then you find your numbers. Carbon-carbon is 347. Carbon-hydrogen is 414. Oxygen double bond is 498. So this is from the table. Carbon-oxygen for carbon dioxide is 799. Now, because this is the products and this is the bonds forming, this is negative. And the oxygen-hydrogen is negative 464. Bonds breaking takes in energy, bonds forming releases. So your bonds forming always have to be negative. You sum everything up and you get the heat of the reaction is 30 kilojoules. So then it says, what is the percent difference between the results? So percent difference will be the absolute value of negative 50 30 minus 5074 over 5074 times 100, and that's equal to, so let's do that together in the calculator. 8.87%. So this is when we're looking at the heat of formation being the true value. And the reason that we're doing that is because this energy, heat of formation, was the amount of energy needed to form carbon dioxide, water, oxygen, and octane. The bond dissociation energy is the energy that's needed to break and form bonds. So we're thinking that true value is the actual heat of formation. So bond energies are an approximate value and do not apply to the molecules in liquid and solid, since that only happens in gas and aqueous phases when they're in solution. Therefore, the more accurate value is obtained from the heat of formation. So that's it for exam overview. I know that I have a tendency to speak like a waterfall, so please go ahead and pause or comment if you need me to re-clarify something, or email me about any other questions. This gives you an idea about all the topics that will be covered, but it might not be exactly this question. Maybe I'll ask you more of a conceptual question than a math question on bond dissociation energy. For lattice energy, on the practice test, it was more conceptual. On the real test, it may be more mathematical. So there's a bunch of different questions that I can ask, but now you know the important material to be covered, so utilize all the different problems to study for the exam.